Welcome to the summer 2020 edition of Design and Analysis of Algorithms. My name is Heather Guarnera, your instructor. Just to briefly introduce myself, if you haven't met me before, I'm part of the Algorithmic Research Lab at KSU, where I do research in algorithmic graph theory. I've also worked as a software engineer in a few industry positions, such as working on flight visualization software for the Navy. I've also worked for local companies designing a graph database language and on the SourceML infrastructure. Now, you may be wondering, why do you have to take this class? The goal is to get you thinking algorithmically, like a real computer scientist. So let me give a motivating example. Let's say your boss gives you a task. You're given the current prices of pork, grain, and other things that might go in a hot dog, and you're given the constraints on what makes a good hot dog. No more than 25% sawdust, anywhere between 5 and 10% ketchup, 5% mustard, etc. And you're asked to make the cheapest hot dog. Every industry asks these type of questions. Now, a mundane programmer might say, okay, I can code, but you have to tell me what to do. This is essentially a typist that knows a programming language. It would be better if you could say, I learned an algorithm that will work for this problem, which I can apply here. But the best scenario is that you can say to your boss, I can develop an algorithm that will fit this specific scenario. This is what we're striving towards. How can you do this? And how can I teach you this? Well, let me take for a moment an example from another industry. Say you need to build a house. First, we need the parameters of the problem. What kind of house will this be? Where will it be located? Is it a beach house, or a winter cabin, or a modern cottage? Each will require different parts. Once you have the parameters clearly understood, you don't start throwing together drywall just yet. You need a design. You need a blueprint. The same concept is true for programming. So what do you need to know in order to be that best version of a programmer? Let's go back to an example of being asked to solve a task. Say you're asked to design an inventory system which can quickly find an item. How would you do this? Let's break this down. There are a few data structures that you could use. Maybe some of them wouldn't be appropriate. So you need to know the parameters of the problem. What do you think would be relevant? We need to know how many items will be stored. What does an item consist of? Does it have a unique ID? Are the items alphabetical? Do they have an order to them? Do we need to find any arbitrary item, or is it just the first and the last one that we put in? Are the items related to one another? Is there a hierarchy to them? For example, maybe this is an inventory for a game. We may want to keep the hierarchy of how an item was made so we could later break it down into those other items. This information will help to narrow down what type of data structure will be appropriate. So now that we have a few data structures which would be relevant to this problem, we need a set of steps which accomplishes the task of finding an item. This can differ based on which data structure we use. So we need an approach to solve the problem. Brute force is one way, just check every item until we find it. But what else is there? In this class, you'll learn a variety of design techniques, along with plenty of example problems and solutions which use those techniques in order to illustrate them. This will give you two things. One, you don't need to reinvent the wheel. With careful evaluation, you may discover that your problem is actually quite similar to one from the survey of example problems and solutions that we'll cover. So you may be able to use it with some modifications to suit your specific requirements. But most importantly, if you have no clear solution, then you can use one of these design techniques and approaches to develop a new algorithm specific to your problem. Now, usually there's more than one solution to a problem. So the next tool that you need is in evaluating which solution is best. First and foremost, it needs to actually work. Sometimes this is obvious that it works, other times it requires more careful rationalization or a formal proof to demonstrate. Secondly, we compare how many resources are required. This includes both memory and time complexity. Now, the amount of time that an algorithm takes can vary significantly depending on the hardware and the environment, like how fast a computer is, what language the algorithm is written in, etc. So first, you need a universal metric for resource requirements. That's where big O notation comes in. It's a way to represent how much time or space is used as a function of the size of the input. Now, comparing running times is reduced to comparing the growth rate of functions. A slow-growing function means that even very large inputs don't take that much time, whereas a fast-growing function means that increasing the size of the input even a little bit can dramatically lengthen the amount of time that an algorithm takes to complete. You'll see a few ways in which you can analyze the complexity of an algorithm. By comparing the efficiency of each solution, we can pick which one is the best. Now, the goal of this class is to get you thinking algorithmically. So as a result of this class, you'll learn how to evaluate algorithms to determine if they work and how efficient they are in terms of time and space, as well as abstractly express an algorithm and its running time. Now, the backbone of any good algorithm is a good data structure. We'll survey a variety of basic and more advanced data structures from the standpoint of their implementation and the efficiency of their operations. For example, what's the difference between inserting into an array and inserting into a linked list in terms of how much time it takes, regardless of the environment? Efficiency should be a priority when you're designing any system. Now, most importantly, you'll learn a set of essential design techniques to help you solve a wide array of unfamiliar problems. These techniques will give you an approach to solve any problem. We'll cover a wide range of fundamental problems and solutions which use these design techniques to demonstrate their effectiveness. So as a consequence, you'll have an understanding of these fundamental problems too. All of this is to get you to think algorithmically like a real computer scientist. This is what will distinguish you from the mundane programmer. This is the difference between a typist who knows a programming language and a software developer or software engineer. Now, this class is not about memorizing a list of algorithms and implementing them. In fact, this isn't a coding class at all. It's about learning design techniques and approaches so that you can apply them to any problem. Because if you can design a solution, the implementation of it is easy. Anyone with basic knowledge of a programming language can take a design and implement it. The difficulty, the true difficulty, and the distinction between you and the mundane programmer is the ability to come up with the design. That's what this class is about, learning how to design algorithms and analyzing them to determine which design is best. So, what topics can you expect to see? Well, we're going to start off with, some math. You'll see how to express an algorithm as pseudocode and count how many steps it takes. We'll revisit some counting techniques like series and summations, and you'll see how to express the runtime of an algorithm as a function. You'll see recursive algorithms, which have a runtime that can be expressed recursively, and there are many common functions that will appear, like linear functions, logarithmic, exponential, and polynomial ones too. We'll see how to use Big O notation to classify the runtime of an algorithm. This will be used as a way to evaluate the efficiency of an algorithm. Next, we'll cover some elementary and advanced data structures. Some of these you've probably encountered already, such as stacks, queues, linked lists, and vectors. The more complex ones may be new to you. What's important for this class is to evaluate these data structures from the standpoint of the efficiency of their operations. Next, we'll start with two of the most fundamental tasks, sorting a list of items or searching for a specific item. These are commonly appearing problems, and there are many approaches to solve them. It gives us an opportunity to see a variety of ways to design an algorithm to solve a problem and how to compare these approaches based on their efficiency. This is all to prepare you for the most important part of this class, fundamental design techniques which can be applied to any problem. Now, these are generic approaches to solving a problem. You'll see these abstractly defined so that you can apply them anywhere, but to solidify your understanding of them, we'll survey a variety of problems which can be solved using those design techniques. So for example, greedy algorithms. These are aptly named due to the fact that these kinds of algorithms make a greedy choice. This is a locally optimal choice, and hope that it will lead to a globally optimal solution. So for example, when you go to the store and you pay for an item which costs $19.01, and you give the cashier a $20 bill, the cashier intuitively uses a greedy approach to return the 99 cents back to you. Rather than returning 99 pennies, he, hopefully, tries to minimize the number of coins returned. So you can pick the largest coin that fits into that 99 cents, which would be a quarter. and then count change up from there, always picking the largest coin. So this is an example of a greedy choice. Each time the cashier chooses the largest coin in an attempt to minimize the total number of coins returned. You'll see examples of this method, this approach, applied to solve problems such as scheduling tasks and other optimization problems. You'll also see the divide and conquer paradigm. The main idea behind this is to recursively break up a difficult problem into smaller, easier to solve subproblems, and then figure out how to use the solutions to those subproblems into solutions for the original problem. Then later, you'll see dynamic programming. Now, the term programming here actually doesn't refer to writing code, but rather to the concept of maintaining a table which is dynamically updated. This paradigm is useful for problems that have many overlapping subproblems. So for example, we could use this to compute the nth Fibonacci number. So if you don't remember the nth Fibonacci number, this is just the sum of the previous two Fibonacci numbers. So for example, if we were to start with, let's say the first and the second Fibonacci number were 0 and 1, if we started with those, we would form the next Fibonacci number as the sum of these two. So it would be 1, and then the next one would be 2, and then 3, and then 5, and then 8, and then so forth. We could keep going. This is one of the more interesting sequences. But if we wanted to compute this nth Fibonacci number, notice that, let's say we wanted to compute the sixth Fibonacci number, we would need to know what the fifth Fibonacci number is and what the fourth Fibonacci number is so that we could add it together and get the sixth one. But in order to figure out the fifth Fibonacci number, we also need to know what the third and the fourth Fibonacci number are. So there's some overlap of problems here. Dynamic programming builds a solution from the bottom up so that these overlapping subproblems don't need to be repeatedly solved. You'll see other applications of this applied to multiplying a chain of matrices together or other optimization problems too. Now the purpose of these techniques is to understand how to apply them to any problem, not just the problems surveyed in this class. Now in the last few weeks of class, we'll turn our focus to a rich and complex data structure, a graph. Now many forms of real-world big data can be represented as a graph. This includes social networks, biological networks, collaboration networks, communication networks like computer or mobile networks, traffic networks like for planes or cars. Now, networks that model the distribution of some commodity, such as how water flows through a water network, or how electricity flows in a power grid, or internet bandwidth, these can be represented with a flow network. We'll also revisit the problem of searching for an item in a graph data structure, and this method also mimics how one would traverse through a maze, and it also gives a way to construct a maze. Finally, we'll see more examples of the fundamental design techniques applied to solve interesting problems on graphs, such as finding a shortest path. This is what your GPS uses to find the shortest route from your current location to the nearest restaurant, for example. This is also used to determine the best way to send a message through a network, which incurs the least delay. We'll also see how to build a minimum spanning tree. This is useful for network design. It answers the question of how to connect all vertices in the graph in the least expensive way. For example, if we want to build a wired connection between buildings on campus so that all buildings are connected, but perhaps connecting the math and science building to the, let's say, liquid crystals building is expensive, much better to connect it first to the physics building and then the library and then kind of work our way around to liquid crystals. This type of problem of figuring out how to build a network using the least amount of materials or the least expensive materials, this can be solved by solving what's called or finding what's called a minimum spanning tree. So these are some of the topics that you'll see in greater detail in the coming weeks. Now, for you to succeed in this course, I would advise that you read ahead. All content is posted on Blackboard and all materials are due each week. I have listed specific due dates for the main topics on the syllabus to help you pace yourself on lecture videos accordingly. These dates correspond to when those topics would normally be covered in an in-person class. Stay ahead of these dates. It is easy, even in a normal 16-week class, to fall behind. It is absolutely crucial during the summer session, which is an accelerated 8-week class, that you do not miss any deadlines. Be consistent and don't leave anything to the last minute. Now, as you work through the modules, try to guess at potential algorithms for solving a problem. When you have a problem formulation, pause the video and think about how would you solve it before you move on to the solution. And when you come up with an algorithm, either in the homework or for your work or for any other purpose, try to look for instances where your algorithm might be wrong. Consider how your algorithm would work on a small example input or in edge cases. And for this class, practice explaining the material, because ultimately you will be tested on your ability to do so. And it helps if you ask questions. I encourage you to post on Piazza regularly, and if you have no questions, check Piazza anyway to help you hone your skill of explaining the material. Piazza will be used for you to both ask and answer questions, and I'll moderate the answers to ensure that they're correct. I'll also have regular office hours during normal class time. We'll meet remotely for the first 10 or 15 minutes of class so that I can check on your progress, but I encourage you to ask questions during that time as well. So this summarizes some of the main ideas of what you'll see in this class, why it's important, and how you can succeed. So you're ready to begin. Go ahead and start the first module.